A single point of light outshines a million suns. This is the baffling reality of ultra-luminous X-ray sources, or ULXs, cosmic engines that defy the fundamental laws of physics as we know them. For decades, these objects have presented a profound mystery, radiating energies so immense they should tear themselves apart. By the end of our journey, you will understand the forces behind these brilliant anomalies and how they are rewriting the rules of the universe. We will explore whether they are middleweight black holes, stellar corpses in a state of extreme gluttony, or something even stranger. What does it feel like to witness a mystery that challenges our most basic understanding of reality? To understand why these cosmic beacons are so perplexing, we must first grasp a fundamental rule of physics, one that these objects seem to ignore. This rule is called the Eddington limit. Think of it as a cosmic speed limit for brightness. A star or a black hole can only shine so brightly before the sheer pressure of its own radiation starts pushing material away. It is a balancing act between the inward pull of gravity and the outward push of light. For a typical stellar mass black hole, this limit is a hard ceiling. Yet ultra-luminous X-ray sources blast past this ceiling with ease, shining hundreds of times brighter than they should be able to. This is not a minor violation. It is a fundamental challenge, as if we watched a car effortlessly travel at 1,000 miles per hour. The engine simply should not hold together. So what cosmic engine are we looking at? They are not the supermassive black holes that anchor the centers of galaxies, and they are not the common X-ray binaries we have studied for decades. They exist in a strange and luminous middle ground, often found within the vibrant, star-forming arms of galaxies like the Whirlpool Galaxy. Their location is a crucial clue, suggesting they are born from the dramatic, short-lived lives of massive stars. By defining what they are not, we narrow the focus onto a truly exotic possibility, forcing us to reconsider how matter and energy can interact in the most extreme environments imaginable. The Einstein Observatory first caught whispers of them in the 1980s, faint signals pointing to something impossibly bright in distant galaxies. But it was the arrival of two new eyes in the sky that truly opened the floodgates. When the Chandra X-ray Observatory and XMM-Newton launched around the turn of the millennium, their vision was so sharp they could pick out individual points of light in galaxies millions of light years away. And what they saw was staggering. Dozens of these brilliant, enigmatic objects were scattered throughout the cosmic landscape, each one a blazing contradiction. Astronomers were immediately confronted with a puzzle. The sheer energy output was far too great for a typical stellar mass black hole or a dense neutron star. Yet these sources were not where a supermassive black hole should be, at the calm center of a galaxy. They were out in the bustling spiral arms among the stellar nurseries. A prime example emerged in the beautiful Pinwheel Galaxy. Its source, known as ULX-1, did not behave like any known object. Its light flickered and changed in ways that defied all existing categories, its spectral signature a complete mystery. This was not just one oddity, it was a pattern. The steady accumulation of these bizarre readings from across the universe created an undeniable challenge. It was a clear signal that our understanding of cosmic engines was incomplete, setting the stage for a fierce and ongoing debate about what exactly was powering them. This fundamental limit is named for the astrophysicist Arthur Eddington, who first described this cosmic balancing act. Picture a star not as a static ball of fire, but as a constant battle. On one side, you have the immense crush of gravity pulling everything inward. On the other, you have the powerful pressure of radiation, the very light being generated which pushes outward. The Eddington limit is the point of perfect stalemate, the maximum brightness where these two titanic forces cancel each other out. For a black hole with the mass of 10 of our suns, this ceiling is an almost unimaginable number, 10 to the 39 ergs per second. A truly colossal amount of energy, yet ultra-luminous X-ray sources do not just approach this limit, they shatter it. We observe them shining 10, 100, even 1,000 times brighter than this theoretical maximum. It is as if a single candle was suddenly outshining a stadium's floodlights. This is not a small accounting error. This is a direct violation of a law we thought was fundamental. So what is happening? The universe is presenting us with a stark choice, forcing us to rewrite the rules. The first possibility is that these are indeed stellar mass black holes, but they are feeding in a way we have never seen. They could be consuming matter at such a voracious, unsustainable rate that they enter a state of super-Eddington accretion. In this frenzied feast, the infalling gas and dust become so incredibly dense and hot that the radiation cannot easily escape. It builds up, creating immense pressure that actually funnels material away in powerful, focused outflows like a pressure cooker releasing steam. This process could allow the central engine to briefly burn far beyond its supposed limit. The second, equally radical idea is that the radiation itself is not shining in all directions, but is being focused into a narrow, intense beam, much like a lighthouse. If that beam just happens to be pointed directly at us, we would see an object that appears far brighter than it truly is on average. Or perhaps the simplest solution is that we have been underestimating the true mass of these monsters. If they are not stellar mass black holes, but instead are intermediate mass black holes, weighing in at hundreds or thousands of solar masses, then their higher Eddington limit would easily explain their staggering luminosity. They would simply be playing by a different set of rules from the start. Each of these explanations requires us to tear up the old textbook and confront the bizarre, true nature of reality under the most extreme gravity the cosmos can muster. Could the key to these brilliant cosmic engines be a missing link in the black hole family tree? One of the most elegant solutions to the ultra-luminous X-ray puzzle is the intermediate mass black hole. These are not the familiar stellar mass black holes, nor the supermassive giants at galactic centers. They are the middleweights with masses ranging from a few hundred to hundreds of thousands of times that of our Sun. This simple change in scale resolves the luminosity problem beautifully. A larger black hole has a much higher Eddington limit, its natural brightness ceiling. An object shining with the ferocity of a ULX would be perfectly normal for a black hole weighing thousands of solar masses. It is not breaking any laws, it is just operating on a grander stage. The evidence for this is not merely theoretical. Astronomers have detected subtle, rhythmic flickers in the X-ray light of some of these sources, known as quasi-periodic oscillations. These flickers are like cosmic clockwork, likely caused by blobs of hot gas orbiting incredibly close to the event horizon. The frequency of these oscillations points directly to the immense gravitational pull of a very massive object, strongly hinting at the presence of an intermediate mass black hole. A prime example is a source known as ESO 24349 HLX1. At its peak, this object shines with a luminosity consistent with a black hole of several thousand solar masses, making it one of the strongest candidates for this middleweight class. The real mystery then becomes one of origins. How does such a black hole form? They could be ancient relics from the very dawn of the universe, collapsing directly from vast primordial clouds of gas. Alternatively, they might be the product of a runaway chain reaction in a dense star cluster, where multiple stellar mass black holes merge over time into a single, more massive entity. Another possibility is that they are the stripped cores of small dwarf galaxies that were devoured by a larger neighbor. If intermediate mass black holes are indeed common within ultra-luminous X-ray sources, they would solve two puzzles at once. They would explain the impossible brightness and, in doing so, fill a crucial gap in our cosmic census, revealing the long-sought middle children of the black hole family. Yet for all its elegance, this is not the only radical idea on the table. What if the objects are not larger, but are instead feeding in a way so violent it defies our expectations? But what if these cosmic engines are not exotic middleweights, but familiar objects pushed to their absolute breaking point? The second leading candidate suggests ultra-luminous X-ray sources are simply stellar mass black holes or neutron stars feeding with a gluttony we once thought impossible. This is the realm of super-Eddington accretion, a state of such violent consumption that the object's own physics are warped. In a standard system, matter spirals inward in a thin, orderly disk. But here, the influx of gas is so torrential that the accretion disk cannot remain stable. It swells and thickens, becoming a seething, puffy torus of unimaginably hot material. At the very center, this chaotic structure can form a narrow funnel, a cosmic nozzle. The intense radiation generated by the infalling matter, which would normally push everything away, is now collimated and focused, shooting out as twin, laser-like beams of X-rays. If our solar system happens to be staring directly down the barrel of one of these beams, we would witness an object that appears hundreds of times brighter than its true average luminosity. The physics are not being broken, they are being focused. We see the glare of a cosmic spotlight, not the diffuse glow of a bare bulb. The evidence for this model is compelling. Astronomers observe powerful outflows, immense winds of particles being blasted away from these systems. These are the telltale signs of a system in overload, a pressure cooker venting excess steam to keep from exploding. The most stunning confirmation came from a famous source known as M82X2. For years, it was a prime ULX candidate, assumed to be a black hole. Then observations revealed a rapid, regular pulse in its X-ray light. This was the unmistakable signature of a pulsar, a spinning neutron star no larger than a city. Here was proof that an object with the mass of our Sun, under the right conditions of extreme gluttony, could shine with the ferocity of 1,000,000 suns. This discovery transforms our view of ultra-luminous X-ray sources. They may not always be strange new monsters, but rather the ultimate expression of known physics, showing us what is possible when matter falls onto a dense core in a truly spectacular downpour. The discovery of a pulse changed everything. Across millions of light years, astronomers detected a faint, rhythmic beat emanating from the hearts of several ultra-luminous X-ray sources. This was not a random flicker, but a precise clockwork signal. In objects like NGC 5907 ULX1 and the famed M82X2, this steady pulse was the unmistakable fingerprint of a neutron star, a city-sized remnant of a supernova spinning at incredible speeds. The implications were staggering. If a neutron star was the engine, then the violation of physics was even more extreme. A neutron star has a much lower Eddington limit than a black hole, a far stricter cosmic speed limit. For it to shine with the power of millions of suns was like watching a single candle outshine the entire sun. How could something so small and dense burn so brightly without instantly tearing itself apart? The answer appears to lie in a force of almost unimaginable power, magnetism. These pulsating ULXs, or pulks, possess magnetic fields that are truly monstrous, trillions of times stronger than the field that protects our own planet. This incredible force does two remarkable things. First, it acts like a cosmic funnel, ruthlessly channeling the torrent of infalling gas and dust directly onto the neutron star's magnetic poles. These poles become searingly hot spots, and as the star spins, these beams of X-ray light sweep across space like a lighthouse, creating the regular pulses we observe. Second, this intense magnetic field may also act as a powerful cage, physically confining the superheated plasma of the accretion flow. It holds the raging inferno together just long enough for the star to sustain its gluttonous feast, preventing the radiation from immediately blowing the entire system apart. This revelation completely rewrites the rules of accretion theory. We are no longer just looking at gravity and light in a balancing act. We are witnessing a three-way battle where gravity pulls matter in, radiation tries to blast it away, and magnetism forcefully contains it all. The existence of pulks proves that the secret to these brilliant cosmic beacons is not always about sheer size, but about the invisible, titanic forces that can shape reality itself at the smallest scales. This brilliant fury is never a solo act. Every ultra-luminous X-ray source is locked in a cosmic dance, a binary system where a dense stellar corpse, a black hole or neutron star, is fed by a generous and often unfortunate companion star. The nature of this donor star is the critical factor that determines the system's immense power. In many of these pairings, the donor is a massive supergiant, a star in the final, bloated stages of its life. Such a star does not hold onto its material tightly. It sheds vast quantities of gas in powerful stellar winds, a constant gale force outflow. Alternatively, if the two stars orbit extremely close to one another, the gravity of the dense object can literally pull material away from its partner. This process, known as Roche-Lobe overflow, is like siphoning fuel from one cosmic tank to another. This stolen material does not fall directly in. Instead, it spirals into a flat, searingly hot structure called an accretion disk, whirling around the central object like water circling a drain. It is within this frantic disk that the true magic happens, as immense friction and gravitational forces heat the gas to millions of degrees, converting its gravitational potential into the blinding X-ray light we observe. The rate of this mass transfer is everything. If the donor star is a truly massive supergiant, or if the binary orbit is exceptionally tight, the flow of fuel can become a torrent. This is what pushes the system into its super-Eddington state, a gluttonous feast where the central engine consumes matter faster than the resulting radiation can push it away. Some of these systems may even be experiencing a brief, extraordinarily violent phase called thermal timescale mass transfer, a period of unstable and runaway accretion that is one of the most energetic events in a star's life. The dance between these two stars, one giving and one taking, is the fundamental engine that creates the conditions for such cosmic brilliance. Without this steady stream of stellar fuel, the fury would simply cease. Yet the raw power of these objects is only half the story. To truly understand what they are, we must learn to read their light, to decode the subtle messages hidden within their brilliant X-ray glow. Every ultra-luminous X-ray source produces a unique spectral signature, a graph of its intensity across different energies that acts like a cosmic fingerprint. This is not a simple, single color of light. It is a complex blend, a symphony of different components that tells a detailed story of the violent processes at work. The first part of this signature is a soft, thermal glow. This is the warmth of the accretion disk itself, the vast, swirling river of superheated gas that spirals toward the central object. The temperature of this disk, revealed by the precise peak of this soft emission, gives us a direct clue about the accretion rate. A brighter, hotter disk often means matter is piling in at a ferocious super-Eddington pace. The second component is a hard power law tail. This is a different kind of energy, a high-energy buzz that typically comes from a region called a corona, a cloud of searingly hot electrons hovering above the disk. When the soft disk photons wander into this corona, they get a massive energy boost through a process called comptonization, slamming into these ultra-fast electrons and being catapulted to much higher energies. The exact shape of the resulting spectrum is incredibly revealing. Some ULXs show a spectrum dominated by that soft, thermal glow. This suggests a system in a state of extreme, puffy accretion, where the disk has thickened and the object is feeding in a glorious, unhinged frenzy. Others display a much harder spectrum, which might indicate a different accretion mode, or the presence of those incredibly strong magnetic fields around a neutron star, which can dramatically alter how the light escapes. Most telling of all, many of these sources show a distinct curve or rollover at the highest energies. It is as if the spectrum hits a wall. This could be the direct observational signature of the Eddington limit in action, the point where radiation pressure finally wins and begins to impede the flow, preventing the highest energy photons from forming. By meticulously modeling these complex spectral fingerprints, astronomers can perform a kind of cosmic forensics. They can estimate the mass of the central black hole, measure the precise temperature of the accretion disk, and calculate the staggering rate at which it is consuming its stellar companion. Each spectrum is a unique data point, a piece of a larger puzzle. By cataloging and comparing them, we are slowly learning to classify these brilliant enigmas into distinct families, moving step by step toward a unified theory that can finally explain all of their impossible light. That rhythmic pulse is only one part of a much larger symphony of light. The way a ULX flickers and changes over time, its variability, is a direct window into the chaotic physics powering it. Some sources display a steady, predictable heartbeat tied to orbital motion or a neutron star's spin. Yet many others blaze with a more chaotic intensity, flickering randomly across timescales from mere milliseconds to many years. These rapid-fire flashes are the signature of raw instability, often caused by clumps of gas colliding within the turbulent accretion disk or sudden shifts in the torrent of matter flowing from the donor star. The most dramatic changes are the state transitions, where a ULX can fundamentally alter its entire character. We observe some of these objects switching between a hard, power law-dominated state and a soft, thermal state, much like the stellar mass black holes in our own galaxy. The crucial difference is that ULXs perform this switch while shining with a luminosity thousands of times greater. A famous example is a source in the galaxy NGC 5407, which underwent a spectacular outburst, increasing its X-ray brightness 100-fold in a matter of days before slowly fading back into obscurity. These are not subtle adjustments, they are cosmic upheavals. By studying the speed of these flickers, astronomers can probe the very edge of reality. The most rapid variability originates from the innermost stable orbit, the final plunging path of matter just moments before it crosses the event horizon, never to be seen again. To track these shifting light curves is to listen to the heartbeat of a monster, a direct audio feed from the brink of oblivion. The very chemistry of a galaxy can dictate the birth of its most brilliant monsters. This hidden factor, known as metallicity, is the cosmic abundance of elements heavier than helium, and it plays a profound role in the story of ultra-luminous X-ray sources. In the grand cosmic cycle, elements like carbon, oxygen, and iron are forged in the hearts of stars and scattered by supernova. A mature, evolved galaxy like our Milky Way is rich with these metals. But in the early universe or in small, pristine dwarf galaxies today, the environment is metal poor. This simple chemical difference has dramatic consequences for star formation. In these low metallicity nurseries, stars can form with much greater masses, colossal beasts that live fast and die young. When such a massive star exhausts its fuel, it does not simply fade away. It collapses, potentially creating a much heavier stellar mass black hole than would be possible in a metal-rich setting. The process does not stop there. A star's metallicity directly controls its stellar winds. High metallicity stars are like cosmic fountains, constantly losing mass as their powerful radiation pushes on the heavy atoms in their outer layers. But a low metallicity star built from simpler, lighter elements holds onto its material with a fiercer grip. It experiences far weaker winds, meaning it retains more of its bulk throughout its life. When this star finally ends its life, the resulting stellar corpse, whether a black hole or a neutron star, is born more massive. A heavier compact object has a higher Eddington limit from the very beginning, granting it a naturally higher ceiling for brilliance. This makes metal-poor dwarf galaxies and the early universe itself a fertile breeding ground for the kind of heavy stellar remnants that can power ultra-luminous X-ray sources. The influence of chemistry extends to the binary dance itself. The donor star in a low metallicity system, having lost less mass to winds, remains more massive for longer. This provides a richer, more sustained fuel supply for its ravenous partner, enabling the kind of super-Eddington accretion that makes these systems shine so fiercely. By comparing ultra-luminous X-ray sources across galaxies with different chemical histories, astronomers are performing a grand experiment. They are learning how the fundamental ingredients available at a star's birth can predetermine its potential for a spectacular, luminous end. This cosmic chemistry set adds a crucial layer of understanding, revealing that the story of these brilliant beacons is not just about gravity and magnetism, but is also written in the elemental makeup of the universe itself. Their brilliant light can cross billions of light-years, offering a glimpse into the far reaches of the cosmos. This incredible reach presents a tantalizing question for astronomers. Could ultra-luminous X-ray sources serve as the next generation of cosmic mile markers? For over a century, we have relied on standard candles, objects with a known intrinsic brightness, to map the universe. The fainter such an object appears from Earth, the farther away it must be. Cepheid variable stars and Type Ia supernova have been the cornerstones of this cosmic distance ladder. Yet ultra-luminous X-ray sources shine with a ferocity that could, in theory, dwarf these traditional tools. Imagine a beacon so powerful it could be seen from the universe's earliest epochs, a potential yardstick for measuring the vast, empty stretches between galaxies. The key lies in finding a predictable pattern within their brilliance. If a specific subclass of these objects, perhaps those powered by neutron stars with similar magnetic fields, consistently reaches the same maximum luminosity, then their observed brightness would directly betray their distance. Alternatively, a unique and repeatable spectral signature, a particular curve in their X-ray fingerprint, could serve as an identifier confirming their true power. The challenge, of course, is their wild diversity. Each system is a unique product of its mass, its accretion rate, and the chemistry of its host galaxy. What appears to be a standard candle might simply be a stellar mass black hole in a state of extreme gluttony, or a middleweight black hole shining calmly at its natural limit. Their light is not governed by a single, simple rule, but by a complex interplay of local conditions, To overcome this, researchers are searching for subtler clues. They are analyzing vast catalogs of ultra-luminous X-ray sources, looking for correlations between an object's peak luminosity and other observable traits. Does its flickering follow a specific timescale? Does the hardness of its X-ray spectrum correlate with its overall power? Finding a reliable relationship would be a monumental breakthrough. It would transform these brilliant anomalies from cosmic curiosities into precision instruments. We could then use them to independently measure the expansion rate of the universe, probing dark energy and the fabric of space-time itself across immense cosmic distances. The quest to understand what they are is slowly becoming a quest to use them as guides, turning their impossible light into a new ruler for the cosmos. Their locations tell a profound story of cosmic life cycles. You will almost always find these brilliant X-ray beacons blazing within the vibrant spiral arms of galaxies or inside the frantic stellar nurseries of starburst galaxies. This is no random placement. It is a direct signature of a recent dramatic stellar event. The massive stars that eventually power ultra-luminous X-ray sources live fast and die young. Their entire lifespan, from birth in a cloud of gas to a supernova death, can be a mere few million years. This is a cosmic blink of an eye. When we see the glow of a ULX, we are witnessing the aftermath of that death, the rebirth of a star's core into a ravenous compact object that is now feeding on its surroundings. The presence of a ULX is therefore a timestamp, a clear indicator of very recent and intense star formation in that region. But these objects are not passive signposts. They actively reshape their own neighborhoods. The incredible blast of X-rays and the powerful particle winds screaming away from the system pour enormous energy into the surrounding gas clouds. This can have two opposing effects. In some cases, this intense radiation can heat the gas and blow it away, effectively sterilizing the region and shutting down any potential for new stars to form. It is a destructive, quenching feedback, yet in other circumstances the effect can be strangely creative. The powerful jets and outflows from a ULX can act like a cosmic plow, slamming G into nearby clouds of cool hydrogen gas. This immense pressure can violently compress the gas, triggering a gravitational collapse that would not have happened otherwise. In these chaotic regions, a ULX does not just signal a past birth, it can actually midwife the birth of the next generation of stars. This creates a complex feedback loop where star death leads to an engine that then governs the conditions for future star life. By mapping the locations of ultra-luminous X-ray sources against maps of star-forming regions, astronomers can decode this intricate dialogue. They see how the rate of new star formation in a galaxy correlates with the number of these brilliant engines it hosts. This turns ULXs from isolated curiosities into vital components of the galactic ecosystem. They are both the products of stellar violence and the architects of future cosmic structure, their brilliant light a testament to the unending cycle of creation and destruction that sculpts our universe. An invisible force sculpts the very brilliance we observe from across the cosmos. This is the power of magnetism, a fundamental cosmic architect that shapes and contains the furious energy of ultra-luminous X-ray sources. For the pulsating neutron stars, the pulks, this role is absolute. Their magnetic fields are not just strong, they are titanic, trillions of times more powerful than Earth's. This incredible force acts as a ruthless cosmic traffic director, seizing control of the chaotic incoming plasma and funneling it directly onto the star's magnetic poles. These two small, searingly hot spots become the focus of the entire system's energy, and as the neutron star spins, these beams sweep across space, creating the precise, clockwork pulses that first revealed their nature. But the magnetic field does more than just aim the light, it provides critical structural support. In a system consuming matter at a super-Eddington rate, the outward pressure from radiation is immense, enough to tear the entire accretion flow apart. The magnetic field acts as a powerful cage, a container of pure force that holds the superheated plasma together just long enough for the neutron star to sustain its gluttonous feast. This magnetic confinement is a key reason these small objects can defy their supposed brightness limit without instantly self-destructing. For black hole systems, the story of magnetism is different but equally vital. Here, large-scale magnetic fields threading through the accretion disk are thought to be the engine behind the powerful jets and outflows we often observe. These fields can twist and snap like rubber bands, launching blobs of charged particles away from the system at nearly the speed of light. Furthermore, the geometry of the magnetic field may be responsible for collimating the radiation itself, focusing the intense X-ray emission into a narrow beam. If our line of sight looks directly down this beam, we witness an object that appears far brighter than it truly is on average. This beaming effect directly manipulates the apparent luminosity we measure, turning a very bright object into an impossibly brilliant one. Understanding these processes requires grappling with magnetohydrodynamics, the complex dance between magnetic fields and ionized, superheated gas. Modeling how these fields behave in such extreme gravity and density is one of the great challenges in theoretical astrophysics. It is a reminder that the secret to these cosmic beacons is not always found in sheer mass or raw power, but in the invisible, sculpting hand of magnetism, a force that can bend light and contain fire on a truly cosmic scale. These cosmic feeding frenzies are so violent they defy simple observation. To truly grasp them, we must step inside a virtual universe built inside the world's most powerful supercomputers. Here, theorists craft intricate simulations, digital laboratories where they can recreate the extreme physics of a super-Eddington flow. They begin with a torrent of digital gas, representing the material stolen from a companion star, and set it spiraling toward a simulated black hole or neutron star. The laws of gravity, fluid dynamics, and radiation transport are all encoded into the equations governing this virtual reality. What these simulations reveal is a dramatic metamorphosis. The familiar, thin accretion disk, orderly and predictable, cannot survive this onslaught of matter. It swells and inflates under the intense radiation pressure, transforming into what is known as a slim or thick disk. This structure is no longer flat. It is a puffy, donut-like torus of searingly hot plasma, so dense that light itself struggles to escape. This is the key to the entire process, a phenomenon called photon trapping. The radiation generated by the incredible friction and heat is effectively trapped within the thick, flowing plasma. Instead of immediately pushing outward and halting the feast, this trapped light is dragged inward with the flow, its energy advected toward the central object like a log caught in a raging river. This allows the accretion to continue at a breakneck pace, far exceeding the normal Eddington limit, but the trapped energy must eventually go somewhere. Near the central object, the geometry of this puffy disk can create a narrow funnel, a clearing in the storm. It is through this cosmic nozzle that the pent-up radiation finally blasts free, not as a gentle glow in all directions, but as a tightly collimated beam of X-rays, a lighthouse beam of pure energy. The simulations make specific, testable predictions. They show that these systems should produce powerful disk winds, immense outflows of material being blown from the surface of the thick disk by the very radiation pressure that shaped it. Remarkably, astronomers have since detected the spectral signatures of these very winds in the light of real ultra-luminous X-ray sources, a stunning confirmation that the virtual laboratories are on the right track. These models also calculate the beaming factor, showing how the apparent, mind-bending luminosity we measure depends almost entirely on our viewing angle. Are we looking directly down the fiery funnel, or are we seeing it from the side, witnessing only a fraction of its true power? By comparing the intricate outputs of these simulations against the flickering, spectral fingerprints of real objects across the galaxy, we are conducting the ultimate test of our physical assumptions. We are not just watching these brilliant enigmas, we are learning to recreate them piece by piece in a quest to understand the forces that allow them to cheat the cosmic speed limit. Our window into this cosmic drama is framed by a silent fleet of observatories orbiting high above our atmosphere. Each one is a specialist, designed to see the universe in a different kind of light, and together they are piecing together the portrait of an ultra-luminous X-ray source. The Chandra X-ray Observatory acts as our sharp-eyed scout. Its incredible resolution allows it to pick out a single, brilliant point of X-ray light from the crowded, star-filled arms of a distant galaxy, isolating the ULX from its stellar neighbors. Once a source is pinpointed, the XMM-Newton telescope takes over as the master analyst. It is a photon collector extraordinaire, gathering enough of these faint, high-energy particles to break them down into a detailed spectrum, the very fingerprint that reveals temperatures, densities, and elemental compositions. But the story is not complete with standard X-rays alone. The Nuclear Spectroscopic Telescope Array, or NuSTAR, extends our vision into the highest energy ranges. It peers into the most violent zones, probing the hard, power law tail of the spectrum to understand the frenetic comptonization process within the superheated corona. For the pulsing neutron stars, the Neutron Star Interior Composition Explorer, or NICER, mounted on the International Space Station, provides a masterclass in timing. It captures the rapid clockwork flickers of these spinning city-sized objects with breathtaking precision, allowing us to measure their spin rates and track how they change as they feed. The view from other parts of the electromagnetic spectrum adds crucial context. The Hubble and now the James Webb Space Telescope turn their powerful optical and infrared eyes toward these regions, identifying the faint, glowing optical counterpart of the donor star and mapping the stellar nursery that gave the system its life. Meanwhile, on the ground, radio telescopes like the Very Large Array often detect the faint, whispering signatures of powerful jets, streams of particles being catapulted away from the system at near light speed. No single instrument can tell the whole story. The true power of modern astronomy lies in this symphony of data. By combining the high-resolution image from Chandra, the detailed spectrum from XMM-Newton, the hard X-ray view from NuSTAR, and the optical context from Webb, astronomers can build a three-dimensional, multi-wavelength model of these chaotic systems. They can see not just the brilliant central engine, but the fuel source, the outflows, and the surrounding environment all at once. This collaborative vision across the spectrum is what transforms a mysterious point of light into a comprehensible, though no less spectacular, cosmic phenomenon. This brilliant fury is born from a cosmic partnership with a finite lifespan. An ultra-luminous X-ray source is not a permanent feature of the cosmos, but rather a spectacular, fleeting phase in the life of a binary star system. Its entire story begins with two massive stars forming together from the same collapsing cloud of gas. The more massive of the two lives a fast and furious life, burning through its nuclear fuel in only a few million years. Its dramatic end comes in a supernova explosion, an event that scatters newly forged elements into space and leaves behind its dense, collapsed core a black hole or a neutron star. The true test for the system is this violent birth. The supernova explosion can sometimes kick the system apart, sending the two stellar remnants flying off on separate paths. But if the binary bond holds, if the two objects remain gravitationally tied, the stage is set for a second act. The system now consists of a compact stellar corpse and its still living, evolving companion star. For a long time, nothing remarkable may happen, but as the companion star itself ages, it begins to swell and change. It may expand into a giant, or it may begin to shed its outer layers in a powerful stellar wind. This is the moment of ignition. The immense gravity of the black hole or neutron star can now begin to pull matter away from its partner. This stolen gas spirals inward, and if the flow is just right, a torrential downpour of stellar material, the system can ignite, crossing the threshold into its ultra-luminous X-ray phase. This period of extreme brilliance is incredibly brief on cosmic timescales. It might last for 10,000 years or perhaps a million. This is a mere blink in the multi-billion-year life of a galaxy. The fury cannot be sustained forever. Eventually, the donor star is depleted, its mass stripped away by its ravenous partner. The binary orbit itself may also slowly change over time, altering the efficiency of the mass transfer. The flow of fuel slows from a torrent to a trickle. As the accretion rate drops below that critical super-Eddington level, the blinding X-ray beacon simply fades. The ULX goes quiet, transitioning into a more ordinary, low-level X-ray binary, or it may fall completely silent into a state of quiescence. Some systems, however, might not be finished. If the donor star has a complex structure or undergoes another internal change later in its life, the mass transfer could spike once more, triggering a new outburst. This cyclical nature reveals that these brilliant objects are not one-time freaks, but natural, recurring stages in the long-term evolution of binary stars. By charting this life cycle from a stellar nursery to a brilliant beacon and finally to a quiet cosmic ember, we do more than solve a puzzle about brightness. We place ultra-luminous X-ray sources into their true context, as vivid but temporary signposts in the continuous, dynamic dance of stellar life and death. The same violent processes that birth these brilliant monsters also send tremors through the fabric of spacetime itself. The most compelling formation channels for the compact objects within ultra-luminous X-ray sources, especially the intermediate mass black holes, frequently involve cataclysmic mergers. When two stellar mass black holes spiral together and collide in the dense core of a star cluster, they do not just create a more massive black hole. They shake the universe, emitting ripples known as gravitational waves. Our current observatories like LIGO and Virgo are perfectly tuned to listen for the final, crashing moments of stellar mass mergers. But the deeper, lower-frequency hum of an intermediate mass black hole merger is a song for the future. A space-based detector called LISA, the Laser Interferometer Space Antenna, is being designed to hear precisely this cosmic chorus. It will open a low-frequency window, allowing us to detect the gravitational waves from black holes thousands of times more massive than our Sun. This creates a breathtaking possibility. If a known ultra-luminous X-ray source is indeed powered by an intermediate mass black hole, its location becomes a prime target. Following a gravitational wave alert from that precise region of space, astronomers could point every available telescope toward it, hoping to catch the flash of electromagnetic light from the merger's aftermath. But mergers are not the only source of these cosmic hums. The extreme dance of a ULX binary itself could produce a continuous, faint signal. In a system with a severe mass imbalance, where a lightweight neutron star orbits a heavy black hole, the extreme and unchanging strain on spacetime might generate a steady stream of low-frequency gravitational waves. This would be like a single, enduring note held across the cosmos. The synergy unfolding here is the very frontier of modern science. we are moving beyond seeing the universe. We are learning to listen to it. The brilliant, impossible light of an ultra-luminous X-ray source gives us a place to look, while the faint whispers of gravitational waves promise to tell us how the object came to be. This is the promise of multi-messenger astrophysics, a future where we do not just observe cosmic events from a distance. We will see their furious light and hear their resonant birth cries at the very same time, experiencing the universe with new senses we are only just beginning to use. Even within the strange family of ultra-luminous X-ray sources, some members are stranger still. A puzzling subclass known as ultra-luminous supersoft sources presents a paradox that seems to defy logic. These objects shine with the same immense power as other ULXs, but their X-ray light is overwhelmingly soft, indicating a surprisingly low temperature. This is deeply counterintuitive. In our everyday experience, a hotter fire glows brighter and whiter, while a cooler one appears dimmer and redder. By that same logic, the incredible luminosity of these sources should come from a region of blistering heat, yet their spectral fingerprint points to a relatively tepid emission. How can something so cool shine so fiercely? Astronomers have proposed two radically different explanations, each pointing to a unique cosmic engine. The first possibility is that we are not looking at a black hole or neutron star at all, but at a white dwarf, the Earth-sized core of a dead star. In this scenario, the white dwarf is pulling matter from a companion and undergoing steady nuclear fusion on its surface. But this is not a standard nova outburst. It is a continuous, super-stable burn happening at a rate so prodigious it outshines any known stellar explosion, creating a sustained, ultra-luminous glow. The second, equally compelling idea returns us to the black hole model, but with a twist. Imagine a super-Eddington accretion disk so incredibly thick and puffy that its innermost, hottest regions are completely hidden from our view. We are left seeing only the cooler, outer layers of this bloated structure, like only feeling the warmth of a bonfire's distant glow while its searing core is obscured by a dense wall of smoke. The very existence of these ultraluminous supersoft sources tells us that our current categories are too simple. The universe is not just creating brighter versions of known objects, it is inventing entirely new kinds of phenomena that operate by rules we are only beginning to glimpse. The brilliant beam of a ULX is not always a steady, unwavering searchlight. It can sway, tracing a slow, cosmic circle over vast stretches of time. This wobble in the accretion disk, a phenomenon known as precession, fundamentally changes how we perceive these objects. Picture a spinning top as it begins to slow down, its axis tracing a slow, lazy circle. Now, imagine that same motion applied to an entire accretion disk, a vast, seething river of superheated gas swirling around a black hole or neutron star. As this entire structure precesses, it carries with it any narrow funnel or jet of radiation that it produces. From our fixed vantage point millions of light years away, this slow dance has a profound effect. The blazing beam of X-rays may swing toward us, making the source appear to turn on in a brilliant flash, and then swing away, causing it to seemingly vanish into obscurity. This creates a long-term, rhythmic pulse in the object's brightness that can repeat over months or even years. A famous example of this exists right in our own galactic neighborhood, a system called SS433. While not always bright enough to be classified as a ULX, it possesses two spectacular, precessing jets that twist through space like a cosmic sprinkler. This tells us the underlying physics is real and can be scaled up. For a true ULX, this geometric wobble is a crucial piece of the puzzle. It means the incredible luminosity we measure might be an illusion of perspective. We might be catching the beam only at its most direct angle, witnessing a fleeting peak of apparent brightness rather than a constant, steady fury. This super-orbital period, as it is called, adds a dynamic, time-dependent layer to an already complex mystery. It forces us to ask a critical question: are we watching the true power of the engine, or are we simply seeing the glare of a slowly turning lighthouse at the precise moment its beam sweeps across our ship in the night? Accounting for this precession is essential because it means the true, steady power of a ULX could be significantly lower than its most dazzling outbursts suggest. These powerful cosmic engines do not just radiate light, they physically reshape their surroundings. Many ultra-luminous X-ray sources blast colossal streams of matter and energy back into space, creating structures that are visible from millions of light-years away. These come in two distinct forms, each telling a different part of the story. The first are the relativistic jets. These are narrow, laser-like beams of charged particles, accelerated to nearly the speed of light and screaming away from the system's poles. We often detect these jets in radio waves, where they appear as brilliant, twin-lobed structures on either side of the central engine. They can punch through the interstellar medium for dozens of light years, inflating vast, glowing bubbles of hot gas. The second form is the wide-angle outflow. This is not a focused beam, but a more general, hurricane-like wind blowing from the surface of the entire accretion disk. Astronomers detect these winds by looking at the object's X-ray spectrum. They see specific absorption lines that are shifted toward the blue end of the spectrum. This blue shift is the telltale sign that the material creating these lines is moving toward us at incredible speeds, a direct observation of matter being physically driven away from the disk. This is the system's pressure release valve. In a state of super-Eddington accretion, the radiation pressure is so immense that it cannot be contained. It must find a way out. These powerful winds carry away a staggering amount of material, sometimes equal to the entire mass being accreted onto the central object. This outflow is not a side effect, it is a fundamental part of the process. It regulates the entire feast, preventing the central black hole or neutron star from consuming matter too quickly and literally choking on its own brilliance. By studying the balance between what falls in and what is blown out, we can measure the true ferocity of the accretion process. These jets and winds are the visible footprints of an invisible force, the intense radiation pressure, actively sculpting the cosmic landscape. They show us that a ULX is not an isolated point of light, but a dynamic, interactive force, one that can trigger or quench star formation, and ultimately govern the evolution of its entire host galaxy. Their brilliant light might be the key to solving one of the greatest timing problems in all of cosmology. At the dawn of time, less than 1 billion years after the Big Bang, we already find fully formed supermassive black holes, behemoths with billions of times the mass of our Sun. Their existence presents a profound puzzle. How could anything grow so massive so quickly? There simply does not seem to have been enough time for them to form from ordinary stellar seeds. This is where the story of ultra-luminous X-ray sources takes a truly cosmic turn. Those brilliant, local engines we study today could be the modern analogues of the very seeds that built the giants. In the pristine, metal-poor environment of the early universe, conditions were perfect for creating monsters. Without heavy elements to drive strong stellar winds, the first generations of stars could collapse directly into black holes of unprecedented size, some perhaps hundreds of times more massive than our Sun. These heavy seeds, these intermediate mass black holes in their infancy, would have been born into a universe rich with fresh, cool gas. They could have immediately begun feasting at a ferocious, super-Eddington rate, shining as the first ultra-luminous X-ray sources in the cosmos. Their high accretion rates would have acted like a cosmic growth hormone, allowing them to bulk up at an incredible pace, rapidly merging and consuming their way toward becoming the supermassive black holes we find at the hearts of ancient galaxies. But their role was not just about growth. The intense, hard radiation pouring out of these primeval ULXs would have blasted through the neutral hydrogen fog that filled the early universe. This powerful energy could have stripped electrons from atoms, helping to reionize the cosmos and clear the way for the transparent universe we see today. We cannot yet look back directly to see those first brilliant beacons. Their light is far too faint and redshifted. Yet by meticulously studying the local ULXs in our own galactic backyard, we are effectively studying living fossils. We are measuring their accretion rates, their outflows, and their growth potential, and we are using that data to build sophisticated models of cosmic dawn. These brilliant anomalies are more than just a local mystery. They may well be the long-sought missing link, the crucial nursery where the universe's most massive objects took their first rapid breaths. Every brilliant point of light we observe comes with a fundamental question: how far away is it truly? This seemingly simple measurement is the very bedrock of our understanding. To know if we are looking at a stellar mass black hole in a state of extreme gluttony or a more massive intermediate monster, we must first calculate its true power, its intrinsic luminosity. And that calculation depends entirely on an accurate cosmic yardstick. For ultra-luminous X-ray sources in our galactic neighborhood, like those within the pinwheel or whirlpool galaxies, we have a reliable starting point. We can use the distance to the host galaxy itself, often measured with trusted tools like the rhythmic pulsations of Cepheid variable stars or the Tully-Fisher relation, which links a galaxy's rotation to its brightness. This gives us a solid foundation, but the further out we look, the fuzzier our measurements become. When a ULX is found in a distant, faint dwarf galaxy, or hangs alone in the intergalactic void, our toolkit shrinks dramatically. Missions like Gaia, which precisely map stellar positions, can sometimes help by identifying the optical counterpart of the donor star and providing a parallax-based distance. Yet for these incredibly distant and faint objects, even Gaia's sharp eyes can struggle. In many cases, the only clue we have is the host galaxy's redshift, the stretching of its light toward the red end of the spectrum due to the expansion of the universe. While redshift is a powerful guide for cosmic distances, it is a blunt instrument compared to the precision of a Cepheid star. It provides an estimate, not a pinpoint measurement. This fundamental uncertainty can warp our entire perception of an object. An inaccurate distance can perform a cosmic magic trick. An ordinary X-ray binary in a nearby galaxy could be misclassified as an ultra-luminous X-ray source, its true power inflated by a miscalculation. Conversely, a genuinely brilliant ULX in a far more distant galaxy might be dismissed as a common object, its light dimmed by the vast expanse we fail to account for. This constant challenge of measurement is a quiet hum in the background of all our discoveries. It reminds us that our most profound interpretations of these cosmic engines are built upon a foundation of metrics that are often fragile, forcing a constant and careful humility in the face of the universe's brilliant, distant light. Behind the brilliant points of light on our telescope images, there are people. This grand cosmic mystery is being unraveled by a global community of astronomers, engineers, and theorists, a human network as complex as the phenomena they study. It begins with the engineers who design and build our eyes in the sky, crafting instruments sensitive enough to catch a handful of X-ray photons from a source millions of light years away. Their work is then handed to observers who spend countless nights, often over many years, patiently collecting the data one exposure at a time. theorists take these precious observations and attempt to recreate the violence within their supercomputer simulations, building virtual universes governed by equations of magnetohydrodynamics and general relativity. For decades, pioneers in this field proposed ideas that seemed almost heretical, suggesting the existence of middleweight black holes or states of accretion so extreme they defied established law. They faced understandable skepticism, their radical models challenged and refined through the slow, meticulous process of scientific debate. This perseverance is the engine of discovery. It requires a rare patience, the willingness to wait years for a single, crucial observation from a space telescope, and a profound openness to paradigms shifting. Today, a new generation is joining the effort, employing sophisticated machine learning algorithms to sift through mountains of X-ray data. These systems can automatically flag strange, flickering objects in distant galaxies, identifying candidate ultra-luminous X-ray sources that might have otherwise been lost in the noise. This collaboration stretches across continents and disciplines, connecting the engineer who polished a telescope mirror with a graduate student who writes a new line of code. It is fueled by human curiosity, by late-night discussions, and by the shared drive to understand the universe's most spectacular performances. The story of these cosmic engines is not just written in X-rays and gravity, but in the collective effort to listen to what the cosmos is trying to tell us. These cosmic engines paint the void with a palette of invisible light. While the raw data tells a story of physics pushed to the limit, the visualizations we create from that data reveal a universe of stunning, violent beauty. When astronomers combine observations across the electromagnetic spectrum, a single ultra-luminous X-ray source blossoms into a complex cosmic landscape. The brilliant central engine, a point of impossible brightness, is often mapped in false color X-ray light as a piercing sapphire or a vibrant violet jewel. This is the heart of the storm, the very source of the paradox. Around it, the optical and infrared eyes of the Hubble and James Webb Space Telescopes unveil the surrounding galaxy. We see great, swirling rivers of crimson gas, vast clouds of cosmic dust glowing with a deep amber warmth, and brilliant, diamond-like clusters of newborn stars. These are the stellar nurseries that gave the system its life, the vibrant context for the central drama. Then, extending far beyond this brilliant core, radio telescopes often capture something else entirely. They reveal the vast, graceful arcs of relativistic jets, colossal streams of particles painting immense, twin-lobed structures on the canvas of space. These jets, visible in subtle shades of orange or red in composite images, can stretch for thousands of light-years, their elegant curves telling a story of immense power channeled and focused over eons. The final composite image is far more than a scientific diagram. It is a work of art, a direct snapshot of the universe's creative and destructive forces intertwined. The processes we analyze, the super-Eddington accretion and the powerful outflows, are not just equations. They are the very brushes that paint these scenes of breathtaking splendor. This aesthetic dimension reminds us that the fundamental laws of physics, in their most extreme expressions, are capable of generating a profound and humbling beauty, a cosmic tapestry where destruction and creation are forever linked in a single, brilliant frame. Their impossible light reaches far beyond the pages of scientific journals, sparking a deep and widespread fascination. We are drawn to ultra-luminous X-ray sources because they are the perfect cosmic riddle, a phenomenon that actively defies our understanding and dares us to look deeper. This is not a settled matter of fact, but a living, breathing frontier. In science fiction, these objects become gateways to alien technologies or natural wonders beyond comprehension, symbols of the universe's untapped potential. Popular science articles feature them as prime examples of how much we have yet to learn, capturing the public's imagination with their sheer, rebellious power. This widespread curiosity is not a mere side effect. It is a vital force that fuels the entire endeavor. The incredible telescopes and supercomputers needed to study these distant beacons represent a massive investment, one often supported by public funding and interest. When a planetarium show projects the brilliant, false-color image of a ULX onto a vast dome, or a documentary narrates the hunt for these cosmic engines, they are doing more than just sharing information. They are inviting everyone into the story of discovery. This engagement is a powerful bridge, allowing scientists to share the genuine thrill of confronting the unknown and to demonstrate why fundamental, curiosity-driven research matters so profoundly. The enduring mystery of ultra-luminous X-ray sources serves as a humbling and exhilarating reminder. It tells us that our cosmos is not yet fully charted, that it still holds profound wonders that challenge our intellect and ignite our innate desire to explore. In their brilliant, contradictory light, we find a compelling reason to keep looking up and to keep asking why. But these brilliant points of light also carry names, long strings of numbers and letters that mark their celestial coordinates. This practical system of cataloging, however, masks a deeper human question: who truly gets to claim a discovery in the vast, shared space of the cosmos? The first team to publish an analysis of a particular ultra-luminous X-ray source often has the privilege of referring to it in their papers. Yet the data itself usually comes from a space telescope funded by many nations. This creates a complex web of credit and collaboration. The effort to ensure fairness is continuous, with international bodies establishing guidelines that recognize both the observers who gather the data and the theorists whose models make sense of the brilliant chaos. This extends to the critical issue of access. The incredible datasets from observatories like Chandra and XMM-Newton are, in principle, a global treasure. But the ability to download, process, and analyze these terabytes of information requires significant technological infrastructure, which can be a barrier for researchers in some parts of the world. Initiatives are now actively working to bridge this divide, creating open data portals and providing cloud-based analysis tools so that a brilliant student in a developing nation has the same opportunity to make a groundbreaking discovery as anyone else. This is not merely a technical challenge, it is an ethical one. The light from these sources has traveled for millions of years, a gift from the universe that does not belong to any single nation or institution. As we decode the secrets of ultra-luminous X-ray sources, we are reminded that the pursuit of knowledge itself must be conducted with integrity and a profound spirit of shared curiosity. The ultimate legacy of these cosmic beacons may not just be the physical laws they reveal, but the model of global cooperation they inspire, uniting humanity in the common goal of understanding our magnificent universe. The next generation of telescopes will transform these brilliant enigmas from points of light into open books. A new era of discovery is on the horizon, driven by observatories of such power they will see the universe in ways we can barely conceive. The European Space Agency's Athena mission, the Advanced Telescope for High-Energy Astrophysics, is a titan in the making. Its colossal collecting area is designed to gather X-ray photons with an efficiency that dwarfs our current tools. This is not just a sharper image, it is a deep, intimate look into the heart of the storm. Athena will perform a kind of cosmic chemistry on the powerful outflows from ultra-luminous X-ray sources. It will measure the composition, the velocity, and the density of these hurricane-like winds with a precision that will finally tell us exactly how much energy is driving them away from the accretion disk. Its superb spectral resolution will act like a superpowered prism, breaking the X-ray light into such fine detail that we can map the temperature and structure of the entire accretion flow, from its cool outer edges to its searing inner funnel. Following close behind is the concept for NASA's Lynx telescope, where Athena gathers immense light. Lynx will see with breathtaking sharpness. Its revolutionary angular resolution will allow it to peer into the most crowded stellar nurseries and resolve the immediate environment around an ultra-luminous X-ray source. We will see, perhaps for the first time, the intricate dance between the jet, the outflow, and the surrounding gas cloud in a system shining from millions of light years away. On the ground, the extremely large telescope will open a complementary window. Its massive 39-meter mirror will collect enough optical and infrared light to study the often faint donor star with unparalleled clarity. We will be able to weigh it, measure its temperature, and understand its evolutionary state, finally identifying the precise type of star that can fuel such a brilliant and violent partnership. Meanwhile, the steady, patient work of the Neutron Star Interior Composition Explorer, or NiSTAR, continues. Its exquisite timing measurements of pulsating ultra-luminous X-ray sources are already revealing how these spinning neutron stars react to immense torrents of matter. Future missions dedicated to X-ray timing will build on this legacy, watching as a pulsar's spin gradually accelerates under the force of accretion, providing a direct measure of the true feeding rate. Together, this fleet of future instruments represents a fundamental shift. We are moving from simply cataloging these objects to truly dissecting their physics. The mysteries that have lingered for decades, the debates over beaming and accretion modes, the true nature of the central engine, all of these puzzles will be tested as never before. We are building the keys to unlock the final chapters of this cosmic story. This brilliant cosmic mystery cannot be solved by a single mind working alone. Unlocking the secrets of ultra-luminous X-ray sources demands a symphony of human knowledge, a collaboration that stretches across the traditional boundaries of science. At its core, this is a problem of extreme physics, where theorists must weave together the intricate laws of general relativity with the chaotic flow of radiation hydrodynamics, modeling how matter behaves when it is simultaneously crushed by gravity and blasted by its own light. Yet the story does not end with equations on a whiteboard. The powerful winds screaming away from these systems carry their own chemical signature, and here the science of chemistry enters the stage. By analyzing the specific absorption lines in an X-ray spectrum, chemists can determine the composition and ionization state of this outflowing material, identifying the very elements being forged and blasted into space. This torrent of data, collected by our most advanced telescopes, would be an indecipherable flood without the crucial work of computer scientists. They develop sophisticated machine learning algorithms to sift through the noise, identifying subtle patterns in the flickering light, and they write the complex code that brings supercomputer simulations of super-Eddington accretion to life. And none of this would be possible without the engineers, the quiet architects who design and build the exquisitely sensitive detectors, the mirrors, and the spacecraft that serve as our eyes in the sky. This collaborative spirit even extends beyond astronomy itself. The study of how superheated plasma behaves under extreme magnetic confinement in a ULX finds a direct parallel in laboratory experiments here on Earth, where physicists work to contain plasma for future fusion energy. The quest to understand a single, brilliant point of light in a distant galaxy becomes a powerful testament to collective human intelligence. It demonstrates that when we focus our diverse talents on a fundamental question about our universe, we can begin to comprehend even its most dazzling and defiant performances. These cosmic engines do more than challenge our physics, they challenge our perspective. To witness a single point of light outshining a million suns is to understand that the universe is not merely large, it is fundamentally extreme. The natural laws that govern our gentle sunrise are the very same laws that permit such brilliant, violent feasts in the void. Here, the end of a star is not a final silence, but a transformation, a stellar death that ignites a new and spectacular phase of life. This endless cycle intertwines destruction and creation on a scale so vast it defies human analogy. Our world, for all its complexity, is a fragile oasis adrift in this ocean of relentless cosmic forces. The sheer commonness of these brilliant objects is a humbling lesson in scale, a quiet reminder of our modest place in the grand scheme, yet within that humility lies a profound wonder. The light from these events travels for millions of years, a message from a distant forge, and we have learned to catch that message. We have built tools to decipher its meaning, using the power of our own intellect to grasp the rules of such magnificent violence. This ability transforms the narrative. We are not just small observers on a tiny rock. We are the part of the universe that has become self-aware, capable of reaching out with our minds to comprehend the brilliant beacons that dot the darkness. Ultra-luminous X-ray sources, in all their defiant glory, are more than astronomical puzzles. They are an invitation to a grander understanding, proof that the cosmos is not only vast and powerful, but also miraculously knowable. These brilliant objects are often misunderstood, cloaked in a fog of popular myths that can obscure their true nature. A frequent assumption paints them as mini-quasars, tiny twins of the active supermassive black holes that power distant galaxies. While both involve matter spiraling into a gravitational pit, the comparison quickly breaks down. A quasar is a galaxy-scale phenomenon, powered by a monster weighing billions of suns. An ultra-luminous X-ray source, in contrast, is a stellar-scale event, a pinpoint engine that could fit comfortably within a single star cluster. Their environments are worlds apart, with one governing an entire galaxy and the other shining within its spiral arms. Another common fear casts these sources as cosmic time bombs, poised to explode without warning. The reality is far less dramatic. These are remarkably stable systems, with lifespans that can stretch for tens of thousands of years. On a human timescale, they are constant, unwavering points of light, not ticking clocks. Their brilliance is the result of a sustained and balanced, if violent, partnership, not an impending detonation. Sensational headlines sometimes label them as mysterious threats, but this is a distortion of their true identity. They are not hostile forces, they are natural laboratories. Located millions of light-years away, they pose no danger to us, instead offering a priceless window into physics operating at its absolute limit. It is also vital to understand what ultra-luminous truly means. This term refers specifically to their phenomenal output in the X-ray part of the spectrum. Their total energy is still vastly overshadowed by the instantaneous, cataclysmic blast of a supernova. A supernova is a single, spectacular explosion, while a ULX is a long-lasting furnace, burning with intense but focused power. Clearing away these misconceptions is not just about scientific accuracy. It is about appreciating these objects for what they genuinely are, not for what sensational stories might suggest. They are not monsters to be feared, but magnificent cosmic experiments, allowing us to witness the laws of nature written in their most extreme and illuminating form. This brilliant quest for cosmic understanding yields profound returns here on Earth. The same extreme science that deciphers these distant beacons actively fuels innovation in our own world. Consider the technology required to catch a handful of X-ray photons from millions of light-years away. the fabrication of the super-smooth, nested mirrors for telescopes like Chandra demanded precision never before achieved. This same expertise in crafting flawless, grazing incidence optics has since been adapted to improve medical imaging devices, leading to more detailed and less invasive diagnostic tools for patients. Similarly, the advanced semiconductor detectors developed to sense faint X-ray signals are now pushing the boundaries of non-destructive testing in the aerospace and manufacturing industries, allowing engineers to peer inside critical components without causing any damage. The challenge does not end with hardware. The sheer volume and complexity of data streaming from these observatories present a monumental analysis problem. To make sense of the flickering, spectral fingerprints of a ULX, scientists must constantly pioneer new computational techniques and sophisticated machine learning algorithms. These data processing innovations inevitably spill over into other fields, from financial modeling to climate science, where managing immense, complex datasets is equally crucial. In classrooms and planetariums, these cosmic mysteries become powerful educational tools. A teacher can use the simple, compelling question of how a single point of light outshines a million suns to introduce students to the fundamental laws of gravity, magnetism, and thermodynamics. The real-world, unsolved nature of the puzzle captures young imaginations in a way that textbook problems often cannot, transforming abstract physics into a thrilling cosmic detective story. This engagement is vital. It inspires the next generation not just of astronomers, but of engineers who will build the next great telescope, software developers who will write its analysis code, and critical thinkers who will solve tomorrow's grand challenges. The pursuit of knowledge about ultra-luminous X-ray sources, while not directly profitable in a traditional sense, is a profound investment in our collective future. It pushes the limits of our technology, enriches our intellectual capital, and cultivates a society that values exploration and understands its place in a vast, magnificent, and knowable cosmos. Their story is a testament to the power of a single, brilliant contradiction. A point of light that defies a fundamental law does not just create a new entry in a catalog, it opens an entire frontier of inquiry. Our journey through the world of ultra-luminous X-ray sources has revealed a cosmos far more dynamic and inventive than we once imagined. We began with the simple, profound puzzle of the Eddington limit, a cosmic speed limit that these objects blithely ignore. That single violation led us down a path of exotic possibilities, from the missing middleweights of the black hole family to neutron stars pushed to a state of glorious magnetic confinement. We saw that their brilliance is never a solo act, but is born from a delicate and violent binary dance, where one star's end becomes another's spectacular rebirth. The invisible hand of unimaginably strong magnetism sculpts their light, while the very chemistry of their host galaxy sets the stage for their formation. This is not a simple mystery with a single answer. It is a complex tapestry where binary dynamics, accretion physics, and galactic environment are all woven together into a single, brilliant point. The ongoing detective work is a global endeavor, a symphony of multi-wavelength observations and supercomputer simulations that slowly peels back the layers of this enigma. These objects are far more than brilliant anomalies. They have become crucial probes, allowing us to test the laws of physics under conditions we could never recreate on Earth. They are potential cosmic mile markers for the distant universe and key players in the cosmic cycle of life and death. They may even be the long-sought seeds from which the supermassive black holes at the hearts of galaxies grew. As we look to the future with powerful new telescopes like Athena and the extremely large telescope on the horizon, The mystery of ultra-luminous X-ray sources promises to yield even more astonishing revelations. They stand as brilliant beacons, reminding us that the universe is not only vast and powerful, but also, and most wonderfully, still full of secrets waiting to be understood.